Okay, good morning. So all these days, what we have done is we have the last 2, 3 classes, we were looking at two medium. Okay, look at this picture here. First of all, you wrote the equation for the electric field as E as a function of Z or Y or whatever it is. So I'm just taking an example, E as a function of Z comma T, and then it is E naught cos omega T minus beta Z. So minus beta Z told you that this wave was traveling in the positive Z direction, but the electric field had an X component. Okay, and we were talking about what will happen when this wave will go and hit the interface between two medium at Z equal to 0. We said part of it will get transmitted, part of it will get reflected, and the transmission coefficient, reflection coefficient, relationship between them, and finding out all the 6 fields: incident, reflected, and transmitted. All these things we have done in the last few classes. Now today what we will do is we were able to write an equation in this form only because there was a single component of the electric field or the magnetic field, or a single component or a single direction in which the electric field was proceeding. But then you need not always have that. Instead, just think of it. If you have your surface, okay, the interface between two medium, and just think of it, if this is my normal, if this is the normal that I'm drawing to both these medium 1 and medium 2, and if I have a wave coming and hitting like this, making an angle theta, then this kind of an incident ray is called a wave incident at an oblique angle. This kind of an incidence is called a wave incident at oblique angle. It is not a normal incidence. It is not in the direction of the normal. So when that happens, what happens is you will be writing a more general expression for the electric field. You will write the electric field as not as a function of x or y or z. You will write as a function of r comma t, and it is E naught cos. Here, just see the change. We have been, remember here we wrote AK. AK talks about the direction in which the wave is moving, or it is the k vector direction. And look at this, beta z. Okay, beta z. Z is definitely a vector. Okay, and when you're writing beta z without a vector form, that means beta and z, there is a that is a dot product is involved. That's what it indirectly says. Or beta itself will have the direction of z. So now when you have to write it as a vector form, you will not write it as beta. You won't write it as beta. You were writing as beta only because you were not writing it in the vector form. When you write it as a vector form, you will have to write E naught cos k dot r minus omega t. So what does this mean? This means that the wave is traveling along the r direction. It is traveling along the r direction. And instead of a beta, you're going to write a vector k. Now, what is this vector k? This vector k is called the propagation vector, or it is also called the wave number vector. It is called the wave number vector because you have studied all in your school days also k is equal to 2 pi lambda. So it is from here that this k vector gets the name wave number vector. And look at this, you're talking about a dot product. If you're talking about a dot product, then this means that k is a vector. And what is r? R is the position vector of a point on the way of the ray. On the way of the wave, okay, if you put a point and talk about what is the coordinate of that point, that coordinate is going to be x comma y comma z, or the position vector is going to be vector r. And now your vector k, okay, vector k or the propagation vector can be written as kx ax plus ky ay plus, here it's ay plus kz az. Or you can talk about 3 components of the propagation vector. Or you can write your k as under root of kx square plus ky square plus kz square. And now what is the significance of this k square? K square is also equal to omega square mu epsilon. K square is equal to omega square mu epsilon. Now, does this not immediately remind you of beta equal to omega into under root of mu epsilon? This we have been using continuously. And this is for a lossless medium when alpha equal to 0. When alpha equal to 0, you have seen for a lossless medium, you have seen that beta equal to omega under root of mu epsilon. Or you come to the conclusion that when the medium is lossless, your beta itself is your k vector. When it is a lossless medium, your beta itself is your K vector. Okay. At other times, you cannot do it. Okay. Please remember, this can be done only for a lossless medium. And this relationship between omega and K, this equation is called your dispersion relationship. Okay. Is this clear, guys? Nothing very different from previous. In previous situation, we were talking about one single direction, so only one component of beta or K was there. Okay, and then it was a normal incident. So you were writing an equation in terms of E as a function of x comma t, or maybe y comma t, or z comma t, depending on what is the direction in which the electric field was, the wave was propagating. But now you're going to write in a more general fashion. This general fashion becomes necessary whenever your wave has to go and hit a surface at an oblique angle. So that's the reason why we are writing this.
Ma'am, this K relation is given, ma'am. That is only for lossless, like omega square mu is only for lossless or any range?
Only for a lossless, this equality holds good. Otherwise, if you remember your alpha and beta, do you remember it was mu epsilon under root of mu epsilon by 2, then you had one big bracket, then under root of 1 minus sigma by omega epsilon whole square, all that complex minus 1 and plus 1 depending on whether it is alpha or beta. All that will come true whenever it is a conductor or when it is a lossy material. Okay, but then when it is a lossless material, what happens is that beta itself, alpha is 0 and beta itself becomes your K. Okay, now let us go ahead. Here, I have last month shared with you an appendix file. There was an appendix A and an appendix B. Okay, now what is done here is the author is not giving the derivation for this. The author is not giving the derivation for this. Okay, but then he gives you how to write. This is an alternate way of writing Maxwell's equation for a source-free region. What is the meaning of source-free? Source-free means sigma equal to 0, rho equal to 0, rho v equal to 0. Oh, sorry, not sigma equal to 0, sorry. J equal to 0, okay? J equal to 0, that means no current source. No current. No current means what? No magnetic field source is there. Similarly, when you're talking of rho v equal to 0, it is volume charge density. Charge is the source for a magnetic, for an electric field. So he says both these are not there. Then you will ask, if both these are not there, previously also, madam, you have told us many places where the source is not there. J is 0, rho is 0. Then how will we have electric field and magnetic field? Now remember, in statics, we have seen that only these two can be the source of electric and magnetic field. But when we went to dynamics, we have seen that a changing magnetic field and a changing electric field can create each other. So they can sustain that way. So you don't necessarily need J or rho. You don't require a current. You don't require a charge. I hope this point is clear to you guys. Faraday's law and Ampere's law would tell you that a changing electric field can create a magnetic field, changing magnetic field can create an electric field. So that is what is happening in an electromagnetic wave. You don't require a source really. So you're talking about a Maxwell's equation when there is no source. Okay, when there is no source, this is one way of writing Maxwell's equation. Can you identify what is equation 3a? Anyone? It's a curl. You can see these two equations are curled. So what is K cross E equal to omega mu H vector? Anyone? Mu H vector is B vector. Please remember. B is equal to mu H. Now does it remind you of something? The right hand side being dou B by dou T. Which is that? Del cross E. What? Which is this one? This is Faraday's law. This is, what is this one? Ampere's law. And then similarly, you can immediately see that this is your Gauss law for magnetism. And this is your Gauss law for electrostatics or electromagnetism. So like this, you can see that, and it is not very difficult to derive this. Okay, all you have to do is, you are going to have that exponential, right? Instead of writing sine or cosine form, if you write the exponential form, what are you going to have? You will have exponential kx minus omega t. So when you do a cross product, you are going to differentiate with respect to X or Y or Z. Therefore, K comes. So that is, are you understanding this, guys? Without really doing it, I can show you. Instead of writing cosine kx minus omega t, okay, if you write e to the power of minus j k, let us say k r, let me write. Oh God. One sec. Yeah. See, electric field and magnetic field can be written as a sine form or a cosine form, kx minus omega t. Instead of that, if I write it in the more general form and write it in the exponential form, I can write it just as I have shown in the previous page. I can write it as k dot r minus omega t. Right? So now think of it. If this is my electric field. Okay. Now, if I have to just go to this equation, if I have to del cross E, when I do, what will I get? When I do del cross E, what will I get? I will be differentiating with respect to X, with respect to Y, with respect to Z. So each time I'm doing that, I'm going to get a Kx, I'll get a Ky, I'll get a Kz. And when I add it, and also remember when I'm doing del, guys, are you following what I'm saying? Think of del cross E. What is del cross E? Dou by dou X of E with an I cap, dou by dou Y of E with a J cap, dou by dou Y of Z, dou by dou Z with a K cap. That's what it is. Okay. So now think of it. If I do this differentiation each time, what will I get here? I will get, when I do with respect to X, I will get KX. KX and the rest of it remains as it is. Then next, when I do it with respect to Y, I'll get a KY. When I do it with respect to Z, I will get a KZ. And then please remember, there is an I cap, J cap, K cap also. So what will all this come together give? All this will together give you your K vector. K vector. So that's the reason why you write on the left-hand side. This is another form of writing Maxwell's equation. So it becomes K cross E. And similarly, the right-hand side, what will you have in, let us say, what will you have in Faraday's law? In Faraday's law, you will have dou B by minus dou B by dou T. Minus dou B by dou T. What is minus dou B by dou T? That is minus mu dou H by dou T. And imagine this exponential form. If I do a time differentiation, what will I get? I will get a minus omega out and the rest will be as it is. And already there is a minus here. That minus and minus will become plus. So I end up getting omega mu H. If anybody has understood this, please unmute and tell me.
It's kind of difficult to understand.
You understood? Okay, nothing. So don't look at this and get worried. If you understand this logic on how this has come, then remembering this equation becomes easy. Okay, and similarly, if you look at Ampere's law equation, Ampere's law in the original form did not have a minus. It had only plus. Remember? It had only plus. It had dou D by dou T on the right hand side. But what is D? D is epsilon E. D is epsilon E. And when you do a differentiation, take this and do a differentiation with respect to time. What will you get? You will get a minus omega out and the same equation. But that minus is what comes out here. So omega. And then what? Then you will ask, madam, what happened to this one? This exponential minus j k dot r minus omega t. That will get cancelled out from the left hand side and the right hand side of the equation. Guys, is this clear now? Then?
Yes, ma'am.
You understood this?
Yes, ma'am.
Yeah, I was able to so that's the reason why, he is just giving another mathematical form. So he does not have to, the author doesn't even think that he has to derive this. But then if you go to Appendix B, I have actually worked it out for you. You can go and look at it. Okay. Now come here. When you come here, next, you look at, you are having three vectors in each of these equations. You are having three vectors, E, H, and K. Okay. Now all these three things are mutually perpendicular to each other. All the three are mutually perpendicular to each other. And what will be the direction of propagation of the wave? Direction of the propagation of the wave will be your K cap direction. K cap direction is the direction in which the wave is propagating. Perpendicular to that, you have electric field and magnetic field. Now, what is the significance of K dot R? What is the significance of K dot R? K dot R is a constant, okay, is a plane. K dot R is a constant, is a plane, and electric field and magnetic field at that point lies on that plane. Like for example, if my wave is traveling like this, think of a plane perpendicular. Think of a plane which is perpendicular like this. I can have any number of planes like this. Okay. Now, K dot R is some constant, signifies one such plane. One such plane. Okay. And on that plane, your electric field and magnetic field. It can be anywhere, but on that plane, perpendicular to each other will be your electric field and magnetic field. So that K dot R is a constant, signifies a perpendicular plane, perpendicular to your K vector. Okay, and electric field and magnetic field will be lying on that plane. Clear, guys? It's slightly difficult to visualize. Okay, but then if you do it, then it's cool. Next, what we'll do is, let us consider our first equation. Let us consider our Faraday's law equation in this form. Take this equation. So this equation is now going to be K dot E, one sec. It's going to be K cross E equal to omega mu H. Okay, now what will be H? What will be H? I can get my mu and H to the other side of the equation and keep only, I can keep my mu and omega to the denominator of the left-hand side. Bring your mu and omega to the left-hand side denominator, then I will get my H. So that's what is this particular equation. Now, this is a cross product between K vector and E vector, and both are mutually perpendicular to each other. Both are perpendicular to each other. So what I can now do is, I can write it as, okay, now let me just write it and show you. 1 by omega mu is there. K cross E. What is my K? K is omega under root of mu epsilon for a lossy medium. And then there is also that AK cap, which is giving the direction, cross E. Right? So this entire thing is your K vector. Okay. So now what we'll do is, let us try to simplify, cancel out whatever can be cancelled out. And so what I will get is under root of epsilon by mu AK cross E. Now, you know that under root of mu by epsilon is eta. Under root of mu by epsilon is eta for a lossless medium. Therefore, you can also write it as AK cap cross E divided by eta. This step is clear to you? So that's how you're getting vector H equal to AK cap cross E by eta. Don't worry, you will use only some of these equations to solve problem. 2 problems when you do these equations, you will remember. Okay, now come to 2 medium. Now comes the real issues. I have a medium mu1, I have a medium 2, epsilon 1 mu1 and epsilon 2 mu2 signify the constitutive properties. And this is my normal. The normal is my z-axis. The normal I'm drawing at the point where the wave is hitting the interface. This is the interface of the 2 medium, and the interface of the 2 medium is at z equal to 0. Okay, and z greater than 0 signifies the second medium. This is my z-axis. This is the origin, let us say. And we have to immediately talk about the electric field, the x-axis and y-axis, you fix it. Now, let's not bother about that right now. I'm just showing you an incident wave. This is my incident wave. Are you seeing the yellow arrow? That yellow arrow and all you won't find in the book. Those are all inclusions. These are all decorations from me. Okay, so you will see my incident ray. An incident ray, you see here, the arrow is there, and I'm writing Ki there. The author has written Ki. I stands for incident. So it is the K vector incident direction. Okay, and let the angle that it is making with the normal be theta I. This is theta I. Okay, and then you're seeing that part of it will get reflected, we have seen. Okay, so it is getting reflected. That reflection is indicated by the blue arrow, and Here we are writing KR. That means a K vector for the R, for the reflected wave. So KR. And there is an angle here. This angle is theta R, angle of reflection. Now you will ask, why did we not discuss all this in the previous case? We didn't discuss all this in the previous case because it was normal incidence. Theta I was 0, theta R was 0, everything was 0. So you didn't have to discuss all that. Next, let us look at the transmitted wave. In the transmitted wave also, the wave, there is a red color arrow there, and then it is written as KT. KT is the K vector for the transmitted wave. Okay. Whereas in the previous problem, we just wrote beta 1 on one side, beta 2 on other side. Okay, we didn't write all this Ki, Kr, Kt on all that because the directions were all the same. There was no problem. At most, it went like this, got reflected, the other went straight. So there was no need for writing all this. Okay, and what is my AN cap? AN cap is the normal vector, and this is the unit normal vector. This is the unit normal vector at the boundary, at the point where it is hitting. Now we define something. Please remember, you have to remember this. Now we define something called the plane of incidence. The plane of incidence. Now look at this. This is my okay. So this is my my plane. This is my plane that is dividing the two medium. A wave. This is my normal. I have drawn my normal AN vector here. My wave is coming like this and hitting. Okay, that means I have drawn an angle theta I. Now this plane, there is a plane here. This is a plane perpendicular to the interface plane. Perpendicular to the interface plane, you can imagine a plane. Okay, now this plane is called the plane of incidence. This plane is called the plane of incidence. And what is defining that plane? Two vectors are defining that plane. One is your incident ray, okay, and the other is the normal. Okay, the plane containing the normal and the incident ray. Okay, so that's called the plane of incidence. And theta is the angle between the K vector there. So K vector there is Ki. Okay, K vector there and the normal. So that angle is called the angle of incidence. And another thing that you will see here, you can just quickly look at it. We have taken the Ki vector and resolved it into two components. Okay, we are writing it as beta t sine theta I is one component. Similarly, here it is beta I incident, no? So it is beta 1, I'm sorry, it's medium 1, so beta 1. Beta 1 sine theta I. Here it will be beta 1 cos, oh my God, I'm not able to see, that's a problem. It's so small, I'm sure you are also not able to see. So this component, okay, the Z component, this is the Z direction. So Z component is going to be Kiz is going to be beta 1 cos theta I. Okay, and similarly, this is going to be, the perpendicular component is going to be beta 1 sine theta I. Similarly, you have written the components for the other two K vectors also. And now let us write three, because previously also you wrote the incident electric field, reflected electric field, and transmitted electric field. Okay, the only difference now is instead of writing just beta z or something, here you have to write x, y, z, and you have to write the components of the K vector. So you will be writing Ki x component into x, Ky component into y, z component into z, like that you will write three equations. Is this clear, guys? So this is the normal, the most general way of writing the electric field vectors: incident, reflected, and transmitted. Okay. Now let's go to the boundary condition.
Ma'am,
yeah.
Did we assume that K is equal to beta, ma'am, in the previous slide?
Yes, we have made that assumption.
Hypertension,
yeah.
Lossless medium.
Right. Lossless, yes. Okay. We are making that assumption.
Okay.
Okay, so let's write this is the most general way of writing the incident electric field, reflected electric field, and the transmitted electric field. Only thing is you're not writing beta anymore. You have to write it in the most general way. So you write it in terms of K, Kx, Ky, Kz, and XYZ. That's it. Otherwise, nothing different. And now, right now, we are also writing omega I, omega R, and omega T. But in last class, we told you omega doesn't change. Frequency will not change. Okay, finally, we are going to come to that conclusion only, that you need not write omega I, omega R, and omega T. It will be omega only. But generally, we are writing it like this. Okay, now let us come to the boundary condition. When a wave crosses the boundary, what will be the boundary condition? We have seen that previously also we have seen that E1, that is the net electric field on the left hand side, should be equal to the net electric field on the right hand side. Similarly for magnetic field, we have written this. Okay, so this was the boundary condition that we have written. And we also said tangential component of the electric field should be continuous across the boundary, we said. Okay, and because the entire field was tangential, we wrote it like this as vector. We wrote like this as vector for normal incidents. Now, when it comes to oblique incidents, let's see what happens. Now, for the boundary condition, now I would rather, you don't waste your time, just take it as it is. If the boundary condition given there has to be satisfied, then all the three omegas have to be equal. That means the frequency should not change because of reflection, because of transmission. So omega will remain the same. Similarly, your components of K, the X component of K for the incident, reflected, and transmitted also should remain the same at the boundary. Similarly for Y-axis, similarly for the Z component. So these you have to take for granted. Only if this is true, then your boundary condition can be true. I mean, just think of it, when at the boundary, okay, at the boundary, at the interface, okay, if the condition has to be true, then this has to be true. Okay, the three components of K at the boundary should be equal for one component. Similarly, take all the three components. That's logic. Okay, next. Now, it further says that this condition 2 and 3 require that the tangential components of the propagation vector has to be continuous. Otherwise, that's exactly what we are saying. No, at the boundary, if K itself has to be the same, that's amounting to say that the tangential component of K has to be continuous. Tangential component of K, if Z is my border interface, the tangential components will be X and Y. Tangential component of K will be X and Y. So 2 and 3 require that the tangential component of the propagation vector is continuous. And this condition is called phase matching condition. It's phase vector matching condition. Okay. And for all this to happen simultaneously, your incident wave, the reflected wave, and the refracted or the transmitted must all lie in the same plane. Have you heard this sometime in optics? Law of refraction, do you remember? Law of refraction when you studied, and similarly law of reflection when you studied also, you have studied in your school days, you have studied that the incident ray and the reflected ray should lie on the same, and the normal should lie on the same plane. Anybody remembers this?
Yes, ma'am.
Yeah, and similarly, when you studied refraction also, you studied the incident ray, then the refracted ray and the normal should lie on the same plane. So this is all coming from this place only, what you studied in optics. Okay, that continuity or the boundary conditions can be satisfied only if this is true. You can't have a situation where, your K is coming like that, and then your transmitted wave is on another plane. That cannot happen. Then continuity is lost.
Ma'am, here how can we say that the K is tangential, ma'am? Because in the normal case, E and H are, we could say that E and H are tangential to the plane. But here, since it is incidenting at an angle of theta, how can we say that those are incident to the plane or interface?
Okay. So if this is your incident,
Okay, ma'am.
okay, if this is your incident, then the other two components will be perpendicular, tangential only.
Okay.
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 Next. And here we are making an assumption that Z is going to be the interface. Okay, now let us come here. So once more, it's the same figure that we have drawn. X, Y, Z we have shown. Okay, now from condition 2, from what is condition 2? Condition 2 is this. Okay, from condition 2. The condition 2 is equating the components of the incident and the reflected transmitted. Okay, so from condition 2, okay, the components, and already you remember we wrote the components here. Components we have written here. Okay, so from condition 2, you will come to the conclusion that Ki sin theta I will be equal to Kr sin theta R will be equal to Kt sin theta T. Do you remember this? This one, and this one. Okay, so those are the X components. This is my X axis if I say in that direction. So the X components will be K1 sin theta I, Ki sin theta I, Kr sin theta R, and Kt sin theta T. Okay, now those three things have to be equal for the second condition of boundary condition, that continuity to be true. Okay, now from this comes out a very interesting result. Just look at this. Incident, reflected. Now these two fellows can be equal. These two fellows can be equal when theta I, okay, no, let's not even go there. Before that, what is theta I? Theta I is the angle of incidence, theta R is the angle of reflection, and theta T is the angle of transmission, or the refraction angle as you studied in your optics. Okay, now let us come here. For a lossless medium, let's again come back to lossless medium. In a lossless medium, Ki equal to Kr, because after all, Ki equal to Kr equal to beta 1, because you are in one medium, in the first medium, and beta 1 is omega under root of mu 1 epsilon 1. Therefore, Ki should be equal to Kr. Now come here, if Ki is equal to Kr, how can these two fellows be equal? The first and the second term can be equal when theta I is equal to theta R. When theta I equal to theta R. We are only saying Ki equal to Kr. We are not saying Ki equal to Kr equal to Kt. Kt is another step son. Okay, so Kt is in medium 2. So it is beta 2. So omega under root of mu 2 epsilon 2. Therefore, you can simply close your eye and say that Ki equal to Kr, but not equal to Kt. Not equal to Kt. And look at this. From this Ki equal to Kr, and from this equation 6 comes this beautiful relationship. What is this one? Theta I equal to theta R. Angle of incidence equal to angle of reflection. This is your law of reflection that comes from here. Okay. Now, similarly, you go to the other one. What was the other one? The other one is Ki sin theta I equal to Kt sin theta T. Ki sin theta I equal to Kt sin theta T. Remember, Ki is not equal to Kt. Ki is not equal to Kt. Now again, assume that it is a lossless medium. If it is a, sorry, assume it is a, oh, I'm going back. Assume it is a lossless medium. If it is a lossless medium, then what happens? Let us see. So you will get omega, okay, omega mu1 I1 divided by omega under root of mu2 epsilon 2. So these two will get cancelled out. So you are left with this. Okay, and this is equal to sin I by sin t. Sin I by sin t is equal to Kt by Ki, which is equal to this. Now from here, look at this. Under root of mu2 epsilon 2 is u2. Because after all, you know that velocity is 1 by under root of mu epsilon. You know this, right? For the lossless medium, you know u equal to 1 by under root of mu epsilon. So using that, you can write this as u1 by u2. u1 by u2. Okay. Next thing, what you do is you multiply and divide the numerator and denominator. You multiply by c. You multiply by c the numerator and the denominator. When you multiply by the c numerator and denominator, what you are going to get will be c by c into under root of mu2 epsilon 2. So what is this? This is going to be equal to c by u2. c by u2. What is the ratio of velocity in free space divided by velocity in a medium? Velocity of a wave in free space divided by velocity of a wave in medium. That has got a name. What is that? Anyone? That is called your refractive index. That's called the refractive index of the medium. Refractive index n is defined as velocity in what? Velocity in free space divided by velocity in that medium. Okay, so therefore from this definition you will get sine theta I by sine theta t as n2 by n1. And what is this? This is your Snell's law. This is your Snell's law. So from the boundary conditions, at oblique angle, you are getting two important laws of optics. Okay, and they are true for these materials, for electromagnetic waves in general. Okay, the two laws are Snell's law and laws of reflection. Okay, so I know a lot has been done. So what we will do is to just reinforce these ideas. Any doubts you want to ask now? Any doubts? Okay, there is no doubt. Let me just quickly go take you down to a problem. Take you to a problem. Right, we are here. Okay, so we are going to do a problem. Let's try this. Read the question, please. Read the question. An electromagnetic wave travels in free space. Free space. So first medium is mu naught epsilon naught. We are not even talking of second medium now, only one medium. Okay, because we have to first get used to the idea of this electric field and this oblique angle. So to make you understand that two problems we'll do. No going to the second medium. So the electric field is given in the form of a phasor representation. It is ES vector equal to 100 e to the power of j 0.866y plus 0.5 z along the ax cap direction volts per meter. So can you recognize some things from here? Anyone? What is E naught?
100.
100. Then what do you think this fellow is? Who is this? Who is this? You remember? Kx, kxx, kyy, kzz. That's why you wrote it as k dot r. Remember? So therefore, you say that this guy is ky. And this one is kz. Okay? This is ky and this is going to be kz. And there is no minus here. There is no minus here. So that means the wave is proceeding in the YZ direction. YZ direction. It's got a Y component and it has got a Z component. That is the propagation direction. So let me write. Propagation is having Y and Z components. Y and Z components. And you're writing ky equal to 0.866 and kz equal to 0.5. Okay. Now, once you have both these guys, can you write your k vector? And kx is equal to 0 because it's not there. You can conclude safely that kx is 0. Now, can you write your k vector, k magnitude? K magnitude will be kx square plus ky square plus kz square. So put it into this, okay? Put it into this, and if you do the calculation, you will get 1 as the answer. K will be equal to 1. I have done it. So I know K is 1. Okay. So I got K equal to 1. The next thing is we are supposed to find out omega. We are supposed to find out omega. So this is free space. Free space means it's a lossless medium. Okay. So therefore, you're making an assumption K equal to beta equal to omega into under root of mu epsilon, but here it is free space. So mu naught epsilon naught. So I will write omega by c. Omega by c. Or you will say that omega is equal to k into c. K is 1, right? K is 1. Therefore, omega is c. And what is c? C is equal to 3 into 10 to the power of 8. And it is omega. Therefore, the unit has to be radians per second. Is this clear? Sri Chakra?
Yes, ma'am, clear.
Is it clear? Okay, please remember, all the time
Yes,
you need
ma'am.
not be given an equation as sine and cosine. You can be given phasor, exponential form without that omega t. Okay, but you should be able to immediately spot what are all the factors given there. Okay, and additionally that minus j, e to the power of minus j is not there. So that means it is traveling, the wave is propagating with a minus y direction and a minus x direction combination. Okay, so that also you have to remember. So you found out one thing. Next, you want to find out lambda. Let's find out lambda also. What is the relationship between k and lambda? What is the relationship between k and lambda? Where is my pointer? Yeah. K equal to 2 pi by lambda. That's why it's called the propagation vector or the wave vector. Okay. So that would imply that lambda equal to 2 pi by k. 2 pi by k. What is k? K is 1. Therefore, your answer is 2 pi or 3.14 into 2. Okay. And it is in meters. So you got your second answer also. Okay, let me check. Yes. Okay, or if you can multiply by 3.2 into 3.14, so 6.28 meter should be the answer. Okay, next. Next, what should you do? You have to find out the magnetic field component. You have ES, and forget incident and all that. We are just thinking it is incident. We are not talking of a second medium for this particular problem. So let us find out the magnetic field. Let's find the magnetic field. Okay. So that means I want HS. HS is equal to what? So now use this formula that you studied together today, Maxwell's equation that you studied. K cross E equal to, anyone remembers? Omega mu H. It's not difficult, yeah. Dou B by dou T, you remember. Dou B by dou T is mu dou H by dou T. And if I do a differentiation with respect to time, I get a omega minus omega. There is already a minus, therefore it becomes plus. Remember it this way. Okay, so K cross E. Now you are having phasor representation, so you can put this. Okay, or from here you get HS equal to 1 by omega mu K cross E, yes. Okay, now you already got your K vector. K vector you had just got some time back. What was your K vector? K vector you had got it as 0.866 a y cap plus 0.5 a z cap. This was your K vector. Okay, and similarly your ES vector was given in the problem. It was given as 100 e to the power of j 0.866 y plus 0.5 z, and it was along the ax cap direction. So look at this. You are now going to do k cross es. It's a cross product. It's a cross product. Now look at this. This is ax cap. Here you have ay cap cross ax cap. What will it be? Ay cap cross ax cap. First, let me write the model, the rest of it. 0.866 into 100 into e to the power of j 0.866y plus 0.5 z. So this is your first term. Now do ay cross ax. What is ay cross ax? Minus az cap. Did you understand this? You're just doing the cross product of these two directions. Now come to the second term. Second term also, let us write everything. It is 0.5 into 100 into e to the power of j 0.866. You don't have to write all this in an examination. To make you understand, I'm writing now. 0.5 z. Okay, now do the cross product ay cap cross, I'm sorry, az cap cross ax. What will it be? X cap cross ax. Ay cap with a plus. So this is going to be your k cross es. Okay, now take this, take out what is common, and then divide by 1 by omega mu. Omega, you got it as 1 by 3 into 10 to the power of 8. Okay, and your mu is mu naught. Okay, and then the rest of it, let us write 100 e to the power of j 0.866y plus 0.5 z is common. Then what is left is going to be minus 0.866 az cap plus 0.5 ay cap. So this is your magnetic field. This is your magnetic field. You can just write mu naught is 4 pi into 10 to the power of minus 7, 3 into 10 to the power of 8. You can put all those values, use your calculator, and then write the final expression for H's. Final expression for H's I have calculated. It is 0.133 ay cap minus 0.23 az cap. Then you have your exponential 100 also I have included. So j 0.866y plus 0.5 z. No need of writing any direction because direction is coming here. Okay, so what can be asked in an examination? In an examination, we can give you the magnetic field and ask you to get the electric field. For that, don't use this equation. Use the equation k cross h. K cross h. There is an equation. Use that equation. That's all. Okay. Only 2 minutes left. Let me just finish up the third part of the problem. The third part of the problem is finding out the time average power in the wave. Time average power in the wave. Please remember, this is lossless medium. This is a lossless medium. Straight away, I'll give you the expression for power average when it is lossless. When it is lossless, you were getting half E naught square divided by modulus eta. So this was your expression. If on the other hand, it's a lossy medium, then you will have a cos of theta eta also will be there, because that is a phase difference between electric field and magnetic field. And if you want to remember how you did this, it was integral p vector, pointing vector over an entire time interval. That is when you got this equation. So just put the values. It will be half into E naught square is there. eta is there. So just put everything. So you will get half, and here you will get 120 pi, you will get, because it is eta naught. And then here you are going to get 100 square. And then you also had that under root of, you had that, you have this part, right? You have this part. So this will also, if you do the under root, okay, if you do the under root of that, you will get a 1. You will get a 1. I did it and saw you are getting a 1. So all that will go off. So don't think that I'm just writing 100 and leaving it, 100 square and leaving it. I've left it like that because the other part, maybe I'll just write it here, because under root of 0.866 whole square plus 0.5 whole square. We already did it when we did k vector, okay, is equal to 1. So that part you need not do. Okay. So this is what it is. I know it is getting progressively difficult. Fellows who don't come to the class are going to get a 0, nothing but 0. Tell them. And go through this recording once, guys. If you have any doubts, I will answer in the next class. Okay, next class, one more problem we'll do without going to the interface of the two medium to make you understand this concept of three-dimensional electric field and magnetic field. Okay, after we do that, then we will do problems on that crossover to the second medium. Any doubts?
Ma'am, do we have this for tomorrow quiz?
No. You go and check now. I have put it on the LMS. The 13 slides of the 10C. 13 slides. I've written explicitly 13 slides of 10C and 10B. Okay. Ma'am, tomorrow is it theory or even sums will be there? Sums means no calculation will be there. And next week, I want to again give you the similar syllabus so that there is a one more revision will be there. Okay, this time you concentrate more on the theory. Okay. Swati has asked this question. I hope it's clear now. So let me just stop recording. Please tell your classmates that they will miserably fail. I drew the histogram and saw I'm getting one cluster like this, then a big gap, and then another cluster like this. Okay. With this, they cannot get anything other than D. No B will be there for this class, I think. Good day.